Have you ever just stared at a function, something like y equals the square root of x plus 2 and then minus 5, and just felt your brain freeze up trying to graph it? Well, what if I told you there's a simple toolkit that lets you take any basic graph you already know and perfectly move it into its final form? No guesswork, no plotting a million points. Let's open up that toolkit and see how it works.
You know, it really all boils down to just three core moves. You've got shifting, which is literally just sliding the graph around. Then there's flipping, which creates a perfect mirror image. And finally, stretching, which, well, it stretches and squishes the graph. These are the big three. Once you get these down, you can basically graph anything.
So, here's our game plan for today. First, we're going to cover what function transformations even are. Then, we'll get really comfortable with sliding functions around with shifts. After that, we'll get into the fun stuff, flipping and stretching. And finally, we'll put it all together into one complete, powerful toolkit.
Okay, first things first, what are we actually talking about when we say function transformations? We got to lay down the foundation before we can start building, right?
So a function transformation is really just a predictable process. We start with a basic, a parent function, think something simple like x squared, and then we apply some very specific rules to it. And these rules move, flip, or reshape its graph into something new. And the most important word there is predictably. There are no surprises here.
All right, let's grab the first and probably the most common tool from our kit, shifts. You might also hear them called translations. This is all about just sliding the entire graph up, down, left, or right without changing its actual shape at all.
Let's start with the easy ones, vertical shifts. Why are they easy? Because they work exactly the way you'd think they would. When you add or subtract a number on the outside of the function, you're directly changing the final output, the y value. So a positive number moves the graph up. A negative number moves it down. It's really as simple as that.
So this is the really crucial distinction we have to make. Vertical shifts change the output, and they just feel intuitive. Horizontal shifts, on the other hand, they change the input. They happen inside the parentheses with the x. And this is where things get a little weird and kind of counterintuitive.
So with horizontal shifts, we're tweaking the x value directly, right inside the function. Look at the formula there. It says f of x minus h. That change is happening right next to the x, before anything else is calculated. And that's what slides the graph left or right along the x-axis.
And here it is. This is the single biggest trap that people fall into with transformations. The logic is totally backwards from what your gut tells you. To move the graph to the right, you actually subtract inside the function. To move it left, you add. Now, why is that? Well, you're solving for the x value that gets you back to your original starting point. So for f of x minus 2, you'd need x to be positive 2 to make the inside 0, right? That's a shift to the right.
Okay, let's try putting this together. Check out this function. Y is f of x minus 3 plus 1. We just have to break it down piece by piece. The minus 3 is times inside with the x, so that's our tricky horizontal shift, which means we go right 3 units. The plus 1 is outside the function, so that's our nice, intuitive vertical shift, up 1 unit. See? That's how we combine these rules to place the graph exactly where it needs to go.
Okay, so we've totally mastered sliding things around. Now it's time to add two more really powerful tools to our kit: flipping the graph, which we call reflections, and reshaping it with stretches and compressions.
Reflections are all about one simple thing. Where do you put the negative sign? If you stick it on the outside of the whole function, like negative f of x, you're making all the y values negative, and that flips the graph vertically, right over the x-axis. But if you put that negative inside with the x, like f of negative x, you're messing with the inputs, and that flips it horizontally over the y-axis.
Now let's talk about stretching. If you multiply the entire function by some number a, you're basically changing its vertical scale. If that number a is bigger than 1, say you have 2 times x squared, you stretch the graph vertically, making it look taller and skinnier. If a is a fraction between 0 and 1, like 1/2 x squared, you compress it, making it look shorter and flatter.
And yep, you guessed it. Just like with the shifts, the horizontal version is counterintuitive. When we multiply the input x by a number, the effect on the graph is the reciprocal of that number. So multiplying by 2 inside the function doesn't stretch it horizontally. It actually squishes it. It compresses it by a factor of 1/2. And multiplying by 1/2, that stretches it out by a factor of 2. It's wild, but it's the rule.
Okay, so we have all the pieces of the puzzle now. shifts, reflections, and stretches. Now it's time for the grand finale, putting it all together to see how we handle functions that have a whole bunch of these transformations happening at once.
So how do you manage all of this at once without getting lost? Well, there's a specific order of operations, just like PEMDAS in arithmetic. The key is to deal with all the horizontal changes first, and then deal with all the vertical changes. And within each of those groups, you always do the stretches and reflections before you do any of the sliding, any of the shifts. If you get that order wrong, your graph is going to end up in the wrong place, guaranteed.
Let's break down a really tricky one. Y equals f of negative x plus 4 all minus 2. Now this is where that order of operations is absolutely critical. Inside the parentheses, we've got both a reflection and a shift. To really see what's going on, you have to factor out that negative. So, negative x plus 4 actually becomes negative times x minus 4. Now we can see it clearly. It's a horizontal reflection over the y-axis, and then a horizontal shift right 4 units. And finally, that minus 2 on the outside is just our simple vertical shift down 2.
And what's really cool is this works in reverse too. Let's say you want to take the plain old square root of x, and you want to move it up 1 unit and left 2 units. Well, you just build the formula yourself. Up 1 means we add 1 on the outside. Easy. Left 2, that's our counterintuitive rule, means we have to add 2 on the inside with the x. And there you have it, our new function g of x is the square root of x plus 2 all plus 1. You are in complete control of that graph.
And here it is, the whole shebang, the entire system all on one slide. This checklist is your ultimate takeaway from all this. It's got every single rule we've talked about, the type of transformation, what it looks like in the algebra, and exactly what it does to the graph. This is your cheat sheet. This is how you're going to master any graph they throw at you. So there you have it. You've got the complete toolkit now. The next time you see some crazy-looking function, you're not going to feel lost. You're going to see the story of its graph, every shift, every reflection, and every stretch that got it there. You've mastered the rules. So the only question left is, what function are you going to transform first?